Did you know that 2 rabbits could turn into over 2.4 quadrillion descendants in just 3 years? That's 2 quadrillion, 442,624,980,786,496 rabbit pairs. No, this isn't some horror movie plot. It's math. And today we're going to solve one of the most elegant problems in computational biology that shows us exactly how fast populations can explode. This is the Rabbits and Recurrence Relations problem from Rosalind. And if you've ever wondered why Fibonacci sequences matter in the real world, you're about to find out. Let's dive in. Hey everyone! Today we're tackling a classic problem that combines biology, mathematics, and programming. Whether you're preparing for coding interviews, studying bioinformatics, or just love a good puzzle, this one's for you. For those who don't know, Rosalind is a platform for learning bioinformatics through problem solving. Think LEET code, but for computational biology. And this problem, it's one of their best. Alright, let's set the scene. Imagine you're a scientist studying rabbit populations and you need to predict how fast they'll grow. Here are the rules. Rule 1, we start with 1 pair of baby rabbits in month 1. Rule 2, rabbits take 1 month to mature, so our initial pair can't reproduce until month 2. Rule 3, once mature, each pair produces k new pairs every single month. In our specific example, k equals 5. Rule 4, rabbits never die. They just keep reproducing, forever. Okay, that last rule is obviously unrealistic, but it keeps our math clean. This is a theoretical model after all. Let's trace through the first few months with k equals 5 to really understand this. Month 1, we have 1 pair of baby rabbits. Total equals 1 pair. Month 2, our original pair is now mature, but they haven't reproduced yet. Total equals 1 pair. Month 3, now it gets interesting. Our mature pair produces 5 new baby pairs. We still have the original pair, that's 1, plus their 5 babies. Total equals 6 pairs. Month 4, the original pair produces 5 more babies because they keep reproducing. The 5 pairs from month 3 are now mature but just became adults, so they haven't reproduced yet. So we have 6 pairs from last month plus 5 new babies equals 11 pairs. Month 5, the original pair produces 5 new babies. The 5 pairs born in month 3, now they each produce 5 babies, which equals 5 times 5, which equals 25 new pairs. We have 11 from last month plus 30 new babies, that's 5 plus 25, equals 41 pairs. See the pattern? This grows fast. By month 36 with k equals 5, we're looking at over 2.4 quadrillion rabbit pairs. Now, here's where we put on our math hats. Let's call f of n the number of rabbit pairs in month n. In any given month, our rabbit population consists of 2 groups. Group 1, rabbits from last month. All the rabbits from month n-1 are still alive, remember, they never die. So that's f of n-1 pairs. Group 2, newborn rabbits. Who can reproduce this month? Only rabbits that were already mature last month. How many mature rabbits were there last month? Well, any rabbit that existed in month n-2 is now mature. That's f of n-2 pairs. Each of these pairs produces k new baby pairs, so we get k times f of n-2 new baby pairs. Therefore, f of n equals f of n-1 plus k times f of n-2. This is our recurrence relation. It's like the Fibonacci sequence's cooler, more productive sibling. Quick comparison. Classic Fibonacci is f of n equals f of n-1 plus f of n-2. Our rabbit problem is f of n equals f of n-1 plus k times f of n-2. That k multiplier makes all the difference. Alright, theory is great, but let's make this computer do the work. Here's my solution. Simple, elegant, and efficient. Let me break down every single line. Lines 1 through 2, the inputs. N equals 36, k equals 5. N is our target month. We want to know how many rabbits we have in month 36. K is the reproduction rate. Each pair produces 5 offspring pairs. Line 3, creating our storage. X equals a list of zeros with n plus 1 slots. We create an array with n plus 1 slots, 0 through 36. Why n plus 1? Because I'm using index I to represent month I, and it's cleaner if month numbers match array indices. Array I will store how many rabbit pairs we have in month I. Lines 4 through 6. Base cases. X of 0 equals 1, x of 1 equals 1, x of 2 equals 1. This is crucial. Let me explain each. X of 0 equals 1. This is a technicality for the math to work. Think of it as our before we started state. X of 1 equals 1. Month 1, we have our initial pair of baby rabbits. X of 2 equals 1. Month 2, those rabbits are now mature but haven't reproduced yet, still just one pair. These three values seed our entire calculation. Lines 7 through 8, the dynamic programming loop. For I in range 3 to n plus 1, x of I equals x of I minus 1 plus k times x of I minus 2. Starting from month 3, we calculate each month using our recurrence relation. X of I minus 1 represents all rabbits from last month that survive. K times x of I minus 2 represents all rabbits that were mature last month producing k offspring. We build up our array, month by month, until we reach month 36. Month 0, base case, result is 1. Month 1, base case, result is 1. Month 2, base case, result is 1. Month 3, 1 plus 5 times 1 equals 6. Month 4, 6 plus 5 times 1 equals 11. Month 5, 11 plus 5 times 6 equals 41. Month 6, 41 plus 5 times 11 equals 96. And this continues until month 36. X of 35 plus 5 times x of 34 equals 2,442,624,980,786,496 rabbit pairs. That's over 2.4 quadrillion pairs from just 2 rabbits in 3 years. Mind blown. Why this solution is excellent. Time complexity. We loop from month 3 to month n doing constant work each iteration. That's O of n time, linear and super efficient. Space complexity. We're storing all n plus 1 months in our array. That's O(n) space. Could we do better? Actually, yes. Here's a space-optimized version. Instead of an array, we only keep track of the last 2 values. This gives us O(1) space, constant memory. For n equals 36, it doesn't matter much, but if n was 1 million, this would be a game changer. You might be thinking, cool math problem, but so what? Well, this exact type of recurrence relation appears in 1. Population genetics, modeling gene frequency changes across generations. 2. Epidemiology, predicting disease spread. SIR models use similar math. 3. Algorithm analysis. Many recursive algorithms have Fibonacci-like complexity. 4. Financial modeling, compound interest with varying rates. 5. Computer science. Dynamic programming is all about storing and reusing these kinds of calculations. The rabbit problem is a gateway to understanding exponential growth, recurrence relations, and dynamic programming. 3 concepts that are everywhere in computational biology and computer science. Mistakes to avoid. Pitfall number 1. Off by 1 errors. Make sure your base cases are correct. It's easy to mess up whether month 1 or month 2 is when they first reproduce. Pitfall number 2. Integer overflow. For large n values, these numbers get huge. In languages like C++ or Java, use long or big integer. Python handles big integers automatically. Another win for Python. Pitfall number 3. Starting loop at wrong index. Remember, we set base cases for months 0, 1, and 2. Our loop must start at 3. And there you have it. We took a seemingly simple biology question, found the mathematical pattern, and implemented an elegant solution using dynamic programming. If you enjoyed this breakdown, try solving it yourself on Rosalind. Try experimenting with different k values. Challenge: can you write the recursive version? Spoiler, it'll be way slower. Drop a comment with your solution or any questions. Remember, the best way to learn algorithms is to code them yourself. Don't just watch, do. Take this problem, modify it, break it, fix it. That's how you truly understand. Thanks for watching and happy coding. See you in the next one.